In this part of lecture number 9, we're going to start developing the strategy we will use to develop the method based on the principle of minimum potential energy. And of course, the first question we need to ask ourselves is, okay, what is the principle of minimum potential energy? To help me explain that, I want you to visualize a complex set of springs. And I've put up a somewhat complex set of springs here. Each spring has its own stiffness, K, and the springs are attached by various nodes, represented by the blue dots, one here, 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 and here. And maybe some of those nodes are attached to an immovable wall, say represented by this large orangish rectangle. So what I'm going to do is I'm going to apply some forces to some of the nodes. And when I do apply these forces, of course, each point in this spring system is going to move some degree based on the application of these forces. That is, I'm going to say that the system or the web of springs is deforming under a load. And of course, when it deforms under the load, each point in each spring now moves or gets displaced by some amount. In the previous classes, we've been calling that displacement in the x direction u, since every point exists somewhere in x and y. U is a function of x and y. And of course, there's v displacement in the y direction, which is also a function of x and y. Now, we're developing a finite element method, which we know is an approximate method. We know we're not actually going to find these functions. We're going to find values for these functions at specific points, specifically the points that we've labeled as nodes in our system. So we will eventually find u1, the displacement at node 1, u2, u3, all the way to u7. And likewise, we will find the displacement in the y direction, v1, v2, v3, all the way to v7. How are we going to do that? Well, we're going to use this principle of minimum potential energy. What do I mean by the minimum potential energy? Well, the first thing we need to understand is when we applied these forces and this object was displaced, there's now potential energy stored in this system. What do I mean by potential energy stored in the system? What I mean is that if I was suddenly to let go or turn off these forces, this system would spring back to its original shape. And in springing or moving back to original shape, it's moving, I can get work out of it. If I can get work out of it, work is a type of energy. Energy can't be created or destroyed. That means the system must have had pent up potential energy stored in the system. All right, now set that aside for a moment. We know there's potential energy built in the system. The question we want to answer is, how much and where do the points in the spring system move to when I apply the forces? It's fairly simple to understand, or at least I think it's fairly straightforward to understand, that node number 7 and say node number 4 that have forces applied to it will be obeying Hooke's law, and they will move dictated based on the size of the force and based on the bulk stiffness of the entire spring system. But they can move to those locations obeying Hooke's law where node number 5 and node number 6, which are not boundary condition nodes and don't have forces applied to them, can move in many different locations and still have node 4 and node 7 move the amount required by Hooke's law. Why do these nodes move where they move? Why does not node 5 move here and node 6 move there? Why not the second time I run the experiment, they move in different locations? Why do they move in the same locations every time? It's not as easy to answer those questions, at least not without knowing something about the universe we live in. So it turns out that if node 5 moves over here and node 6 moves over here and node 5 moves over here and node 6 moves over here, for each different combination of movements, the amount of potential energy stored in the system will be different. For every possible combination or set of deformations possible in the system, there will be a different amount of potential energy stored in the system. It turns out that in the universe that we live in, the amount that node number 5 and node number 6 do move will be the amount they move that will create the minimum amount of potential energy in the system. And so the principle of minimum potential energy states that among all admissible sets of displacements that a body can assume, the one that minimizes the total potential energy stored in the body will be the true set of displacements. Now, I should take a moment to explain what I mean by an admissible set of displacements. An admissible displacement is any set of displacements that satisfies boundary conditions and continuity. So boundary conditions is fairly clear. Obviously, I can't have nodes number 1, 2, and 3, which are attached to a wall, move. That's not an admissible displacement. I also can't have a point at the very end of spring 3 move in this direction, and at the very end of node 7 move in this direction, because I need continuity at node 5. So maintaining the continuity of the problem is also a restriction. Okay? So now that we know what the principle of minimum potential energy is, how are we going to use it to derive our method? The first thing we're going to do is we're going to develop a formula for or a function for the potential energy stored in the system. And in this class, we will use this symbol, pi sub p, for potential energy. And this potential energy stored in the system is a function of all of the displacements in the system. That is that the total potential energy in the system is a function of u, which of course is a function of x and y, and it's a function of v, which is also a function of x and y. Now, stated this way, where potential energy in the system, rho sub p, is a function of two other functions, that's what in what's called variational calculus is called a variational. But we're not going to need to look at or understand variational calculus in this class to develop our method, because we're not looking at u as a function of x and y. We're looking to find the values of u and v only at specific points. So what we're going to do is we're going to find a function for total potential energy in the system as a function of the displacements at the nodes, u1, v1, u2, v2, etc., all the way to u7 and v7. We will then try to minimize the value of this function with respect to these variables using methods for minimizing a function that we learned in our elementary or introductory calculus courses. And we'll start going into the details of that in the next few videos.